All right, so now we want to start looking at the quality of the data that we collect in an experiment by comparing our measurements within the experiment to each other. So first measure of variability is to look at the spread or the range. So let's imagine that we have two data sets taken in two different experiments. And we want our data to spread from 0 to 8. How about a 4, and how about a 2 and a 6? So since we have two experiments that we're going to look at, let's go. And once I've collected all of my measurements and put them onto a histogram, I discover that they both center at 4. And I further discover, luckily for me, that they are both very symmetrical curves. Or distributions, I guess. So this would be a very symmetrical distribution of a sample set. And let's say in both cases, n equals 30 and n equals 30. So there's not a lot different between these two sets so far, but what if this set broke into a wider dispersion, or excuse me, a distribution, a wider distribution. All right, so we can see that all of the data points in this first example are very close to the center, while the data points in this second example spread farther away from the center. And so spread matters in this case. It tells us something about the information. It's not good or bad, but it is information about our experiment, about the quality of the information that we've gathered from our experiment. And this measure of variability within an experiment is called the range. I'm not sure I made it really clear. The measure of variability isn't actually between two experiments. I'm not comparing this experiment to this experiment. I'm just looking at the data in an experiment, finding out how far the data spreads out, and that gives me information. Sometimes I want something to be really tight like this, things that matter with size. So, for example, if you're a manufacturer that makes bolts, for example, and you have 4 different machines manufacturing a 1/4-inch bolt, you would want, in the aggregate, all of the bolts that come out of your machine, out of your factory, all of your 1/4-inch bolts to be really close to exactly 1/4 inch. So you would want the spread of your data to be super close as you take a random sample of those bolts coming out of your factory and measure them to see that they are actually 1/4 inch wide or in diameter. So sometimes you want really close measurements. Sometimes you want really spread out measurements. For example, we see this on testing. Imagine if when I gave you a test, if I said from 98 to 100 is an A, and from 96 to 98 is a B, and then on. So what would that give us? C would be down to 94, and a D would be down to 92. So anything 90 and below, anything less than 90 would be an F. That would be crazy. You wouldn't want the information or the data points, the raw score on a test, to be all crammed up really close. You want to spread out so that you have a fighting chance, or at least so that your comparisons make sense. Because is there really that much of a difference in comparison from someone who, for example, gets a 96 to a 90? Is there the difference of a B to an F in that comparison? And there is not. So some experiments, you really do want your actual results to be spread out. Some experiments, you want your actual results to be really close to the center. In either case, a number that's really useful in imagining how good your data is called range. And range is just what is the spread from beginning to end in units. So in this case, the range would be from 2 to 6 is 4. And we find that by taking the largest value and subtracting the smallest value, 4. So we can say the range for this piece of information or this experiment is 4, where the range for this experiment is 8, take away 0. So the spread in this experiment, or the range in this experiment, is 8. So while the range is useful, it's not very informative about the quality of each measurement. And so there's another form of measure of variability that looks at the quality of each measurement individually and then takes those as a whole. So let's look at one of these up closer. So suppose I have a data set, n equals 5, and the values for n are 5, 7, 1, 2, 4. If I were to put these onto a dot plot, remember a dot plot is just the number line, which gives me a position for each value in my set. So 1, 2, 3, 4, 5, 6, and 7. So for this, if I take each point and just represent it as a dot on this plot, or on this, along this number line. So what I have now is a representation on the number line of where each of my elements are. But first, let's calculate the mean. So remember, x bar, the mean, is the sum from the first to the nth, in this case, 1, 2, 3, 4, 5 elements, from the first to the fifth measurements, all divided by n, in this case is 5. So that gives me, once I take the sum of all the parts, I have 7, 10, 15, 19 divided by 5, which is 3.8. So that means right here, almost at 4, is where my mean falls. So now what I want to do to measure my variability is I want to measure each point as a distance from the average. So this point is almost at the average. 4 is almost there. And that distance, easy to see, is 0.2. You can see already that there's no way I can write this here on my picture. So I'm going to make a table to keep my data straight. So first, let's go with my values, and I think, let's see, 5, 7, 1, 2, and 4. So I'm just going to list the points, and then I want to find each point's distance from the average or the mean. And so to find distance, we remember from all the algebra we've done all these years, is I'm going to subtract the average from this point. So if I want to know the distance from 5, or from the mean to 5, I can take 5 minus 3.8, and that'll tell me exactly how far away from the mean the number 5 is. So this is 1.2. Let me see, maybe I should put my arithmetic in so you have it in your future notes. So this would be 5 minus 3.8 equals 1.2, and then 7 minus 3.8 equals 3.2. 1 minus 3.8 equals negative 2.8. 2 minus 3.8 equals negative 1.8. And 4 minus 3.8 equals 0.2. So all I've done is look for what is the actual distance of each point from the average or from the mean. And I have found that distance by using this calculation, which measures the deviation of each individual measurement from the mean. So this is deviation. Let's look at where we are. There's some population out there, some population of numbers. Let's just say they're numbers right now. So from a population, I took a sample. And that sample consists of 1, 2, 3, 4, 5 measurements. So when I start looking at the quality of my experiment, right, so the measure of variability in my experiment, I can certainly figure out the range. My smallest number is 1, my biggest number is 7, and so the range is 7 minus 1 equals 6. And that tells me that the data, the measurements in my sample, have a smallest value to a largest value within 6 units of each other. Useful, not complete, but definitely useful. Then if I look individually at each measurement, I'm able to get some number of deviation for each measurement. So I can decide for each measurement, like remember yesterday in the Kobe Bryant example, is Kobe Bryant an outlier, or is Kobe Bryant kind of within the realm of the actual range? Does he throw off my data, or is he within my data and he just happens to be one of the larger values? In this case, I can look at each individual, but I can't really look at my sample. Like, it would be nice if I could reduce my sample to some measure of variation. And in fact, I could just take the average of all the deviations. I could add them up and see what the average is. But in this case, when I take the average, I'm going to get 0. So if I add all of these values up and divide by 5, the result is 0 for my average or my mean. Well, that's obviously not very useful. That says that the average of my data is all right on my mean. That's not a useful piece of information. And the reason I get this weird 0 is because of all these pluses and minuses, right? So when I sum or add these all together, some of them are going to 0. Well, they're all going to 0 each other out because I have negatives and positives. So we could think instead to take the absolute value. If I were to take the absolute value of all of them, it does give me a result that no longer eliminates the negatives, but just tells me in actual distance from my mean how far away are my points, and that's really what I want. So absolute value sounds like an amazing choice. I don't know why. I do know why. It is actually easier to do it this way. But in stats, we don't use the absolute value. We go about it a different way. First, we square all of the numbers to make them positive, and then we take the square root built into the calculations. So it's, in the long run, once you learn the calculations, what you're doing is you're squaring it to make it positive, then taking the square root, giving you the absolute value. But when you're calculating in formulas, it's easier to do it this way. So let's look at that calculation next. If I took the deviation and square it, then I get 1.44, 10.24, 7.84, 3.24, and 0.04. And when I average these, I get 2280. Oh, not when I average them, when I sum them, when I add them all up. I get 2280, 22.80. From this number called the sum of squares, which is just adding up the squares of all of the deviations in the sample. The sum of squares, will use this value to calculate the variance of this sample. So an equation for the variance, it's called S squared. So S squared means variance. It actually means sample variance, because we want to be able to distinguish between when we're working with an entire population and when we're working with only a sample from the population. So the sample variance has a formula. S squared equals the sum, that's that Greek sigma, the sum of all of these values divided by the number of measurements minus 1. So it's not really a pure average, is it? It's not a pure average because we're not dividing by the number of elements. We're not finding the sum of all of the values and then dividing by the 5 elements we have. We're dividing by n minus 1. And if you bear with me, I will explain it to you in just a moment. So this is a sample variance. We also want to have a population. We have a formula for the population variance. So at some point, we'll be working with populations rather than samples. And when you're working with a population, just to make it obvious that that's what we're doing, we change up the notation a little bit. We do the same thing, we just change up the notation a bit. So instead of S squared, we use sigma squared. So this is a Greek lowercase s. So sigma squared is the symbol that we use when we're talking about population variance instead of sample variance. And the formula is very similar. It's the sum of all of the elements in the population minus mu. And remember, in yesterday's video, I told you that mu is the symbol we use rather than X bar when we're talking about a population. So the mean for a population is mu, the symbol is mu, and the mean for a population, for a sample, the symbol is X bar. They're still the averages. Over here, this is still the variance, but we just use a different symbol because we're talking about a population. And this time we're going to divide by all the elements in the population using a capital N. So it turns out that when we try to estimate the population variance from the sample variance. So you run an experiment, it's a really good experiment, you get a good cross-section of measurements, and you calculate the variance for the sample. When you try to extrapolate to the population variance, over time it's just been discovered that n minus 1 gives you a better estimate. That's the only reason for using n minus 1 in the denominator. It just turns out that that gave a better estimate over time, and that's why the formula is that way. And last but not least, standard deviation. Remember when we talked a long time ago up here, what we really wanted to do was find the average of all the distances from the mean. If we could average out these distances, it'll give us some idea of how closely our data matches, in general, matches our mean. Like up here with these histograms, right? This data is super close. The deviation of this data would be smaller than the deviation of this data. And when we say standard, what we're talking about is just standardizing that distance, making it something that references the average of the whole set rather than each individual piece. And so standard deviation is the divide out by, or is the get rid of the square part. Because remember, we started with a value, just the absolute value of the distance, and then we squared it to get rid of the negatives, and now we have to unsquare it. So once you have the variance squared, whatever that value is, standard deviation is just square root it to get us back into the range and the size of numbers that we're talking about. So the square root of the variance gives us standard deviation. So let's just finish out our calculations here. For this set that we worked with, we can now say that our sample variance is 22.8 divided by n minus 1. I have 5 elements, so I'm going to divide that by 4, and that tells me that my variance is 5.7. Right, so my S squared, sorry, dog walking around, S squared equals 5.7. Then take the square root of that value, and it tells me or gives me my standard deviation, which is just S, standard deviation, equals 2.38746. So let's round to the hundredths. So let's say 2.39. So I now have my standard deviation for my sample set. I have my variance for my sample set. I know my sum of squares or my deviation for each individual element, and I know I know my sum of squares for the individual element, which was determined by squaring each individual deviation for each individual element, and this is all for the sample. Later we'll learn how to extrapolate this information into population variance.